Welcome to eCraft. We are glad to have you here. This video is a recorded training session that introduces Arduino to fresh engineering graduate students. This is the third part of the video, which focuses on the analog input functions available on the Arduino UNO R3 boards. The previous parts of this series of videos have already been posted on this channel.
So as I mentioned that this particular microcontroller has analog to digital converter or ADC inbuilt inside the microcontroller, and that's a single channel ADC, though it's a single channel ADC, but it has a multiplexer in front of it so that it can multiplex 6 analog channels connected to the port C pin 0 to port C pin 5 of the microcontroller. Basically, those are the AD inputs of Arduino, right? So if you see the Arduino board, so you see this A0 to A5. So these are the port pins where you can connect the analog input, and you can read those analog inputs using your ADC. And there is an internal multiplexer and the ADC. So we'll look at the ADC architecture a little bit, and you can connect any analog input here, and you can read the value inside the microcontroller using the ADC, and that is a 10-bit ADC. Okay, so it's a 10-bit SAR type ADC. The digital world is 0 or 1, right? So either you have an on or a off. So now how we can express analog voltage using the digital value. So suppose you have 0 or 1, and you have two levels. You have an analog voltage which is varying between 0 volt to 5 volt. So this is called full scale, right? So the minimum and maximum value in between, this analog voltage can vary, and that is called the full scale. Like, what is the full scale? It's maximum to minimum difference. That's the full scale. Now if you have 0 and 1, then you can have only two levels. Now if you suppose this is a waveform, okay, let me draw this in another color. So suppose this is the waveform. Oops. Okay, let me suppose this is the waveform. You can see this green one, right? So it's a slope basically. I wanted to single line, sorry. This is the waveform. It's just a voltage varying from 0 to 5 volt linearly, right? But if you have only this 0 and 1 as the option, then what will happen? If you see in time, so we are seeing in time, right? So this x-axis is time. So this voltage is varying from 0 volt to 5 volt linearly over a period of time. So this is T1 and this is T2. Right? And you start reading from here in your digital logic, and you see, okay, I am still 0. Right? So your digital logic says, okay, I'm still 0 here, still 0 here, still 0 here. At some point of here, okay, now I detect a high, right? So your digital response. So if you convert this analog into digital, your digital waveform will be like this, right? So you'll have you'll have 0 here, and then you'll have 1 here. So you basically get two levels of the analog voltage. So this portion, though it has multiple voltages, like it's 0, then 0 0.1, 0 0.2, 2.1, like that. So up to 2.5 maybe. But you see in your digital world, you see all this as 0. Okay, this is not very good, right? So okay, let us increase this by 2 bits. So let me represent this using 2 bits. Now you can have 0 0. You can have 0 0. Then you can have 0 1. Then you can have 0 2. I'm sorry, 1 0 and 1 1, right? So I now have four values. So what I will do now? Okay, great. So I have four levels, and I'm going to represent that analog voltage using those four levels. So what will happen is, okay, I see that till this level I see 0. Okay, then if I can detect this level, right, this threshold, then I see, okay, I now get, so this was 0 0. Okay, now I have got 0 1. Okay, here I see another transition, and okay, this is then 1 0, and maybe here I see, okay, now I have reached the full value, so this is 1 1, right? So this is little better than this, right? So this is not at all good, but this is little better. Now imagine if you have a 10-bit ADC, like you have 10 bits. So this is only, you got 2 bits, right? You got 2 bits, and this is only 1 bit. So it can have either 1 or 0. So it can have permutation combinations of zeros and ones. So it is 0 0 0 1, 1 0 1 1. So you have 4 states, you have 2 states. So if you have a 10-bit ADC, how many such states are possible? Can somebody answer? It's very easy question. So you now have 10 bits to represent a signal. So how many states this can have? Here you can have 4, right? So basically it's 2 to the power 2. Here it is 2 to the power 1, right? So it is 2 to the power 10, right? So that you can imagine, it's a huge number of steps, right? So that way you can happen, like you can very closely, you will be able to represent this analog value into the digital values, because you will have more number of steps. How many number of steps? 2 to the power 10, right? So you can express this full scale range of the ADC in 2 to the power 10 different transition levels, and that will make your signal much closer to your analog signal, right? So that will look something like, okay, okay, I think I haven't shown that picture here. Yeah, that I haven't shown here. So just imagine that you have a sinusoidal waveform, and you are able to have 2 to the power 10. It's a 10-bit ADC, and your sinusoidal signal will look like this. But in digital form, it will be like, it will be something like this, right? Sorry, it's a kind of stepped signal, but it's kind of you are getting all these steps because you are having discrete steps. Basically digital is nothing but you have discrete values, but still the gap between the two transitions is much less, as your number of bits of ADC keeps on increasing. If you have a 16-bit ADC, then that is even much better, right? So this is called the resolution of the ADC. Okay, how much resolution you have for the ADC? So more resolution, you are able to convert your analog signal in more kind of very close to the analog world in the digital world. So it will be 2 to the power 16 steps you can have. You can express this full scale range into 2 to the power 16 digital transitions, so which is much better. Even you get ADC with 24 bits. So those are highly accurate, high resolution ADCs basically. But again, more number of bits or more resolution will slow down your ADC also. The conversion time, something is called as the conversion time. The conversion time will go up. So the more resolution ADCs will be slower, and less resolution ADC might be faster. And that too, there are various types of ADCs, like SAR is one, successive approximation type. register type ADC. So SAR type register is very fast and not very accurate as sigma delta. But I'm not going into those ADC topics because that anyway will be covered during your curriculum. But just know that the ADC inside this Arduino is a SAR type, and it's a 10-bit ADC. So the resolution is 10-bit. So you can have 2 to the power 10 steps or transitions, different voltage transitions you can have, right? But just try to understand the concept of the resolution right now, which is 10-bit. And then there is another concept called the voltage reference. So the ADC again will be able to convert your analog input voltage with respect to some reference voltage only, right? Because the reference voltage will determine the full scale range for the ADC. Like this full scale, whether it is 0 to 5 volt, or it is 0 to 2.5 volt, or 0 to 1 volt, etc. It will try to understand with respect to some reference voltage which you apply to the or you configure for the ADC, right? So Arduino, in the Arduino, the ADC what is built in, it has three options. One is that you can set the reference as an internal 1.1 volt reference. So basically your full scale will be 0 to 1.1 volt, which is shown like this. So your all input signal has to be within this scale, right? If something goes above, what will happen? It will go into saturation. So basically your ADC will still read this high value, right? Where what is the this value, this will also only be read if your signal goes above this. Then you can set the voltage reference as an external reference which you can connect to the a ref analog reference pin. So that is pin number, there is a pin on the Arduino board. So as you could see, this pin ARF here, ARF, this pin or this pin, right? So this is a pin to connect the external analog reference. If you are trying to use a shield board which needs a different reference, and you can connect an external analog reference, and there you can select the reference from 0 to I think 4 volt. You can keep any of these voltages as a reference, and then your signal can vary between 0 to 4 volt, or by default is the AVCC. AVCC is 5 volt basically for Arduino UNO. So basically the supply 5 volt, and your default range is basically set to 5 volt. So if you are not much bothered about the other two, you can keep it by default setting, which is 5 volt, same as the power supply, the supply of the ADC. So then your signal can vary between 0 to 5 volt. Your input signal, analog input signal, can vary between 0 to 5 volt, and you have the 10-bit resolution. So that will be divided into 5 volt divided by 2 to the power 10. So that will be your LSB, which is called least significant bit. But right now what I'm going to do is I'm going to do a quick example on how to read the ADC from the Arduino, so that you can appreciate, even you don't need to know all this stuff, like all these register selections and stuff like that in detail in order to use the ADC of Arduino UNO. You don't need all those stuff to program an Arduino UNO, right? So the best thing what you need to do is go to the file example, and then you have an analog section, right? Go to this analog input example. Okay, so lots of comment mentioned. You can read it once if you need. But the basic thing is that, see, it has defined sensor pin as A0. So basically connect the input to the A0 pin of Arduino UNO. Your LED pin is still that 13, which is the built-in LED, and there is a sensor value, which is basically the variable for the ADC output, right? And so in setup, what they have done is, again, the LED pin they have configured as an output pin, because by default it will be input. For Arduino UNO, the A0 is always an analog input pin by default, so you don't need to set it up. But you can also do that same in the setup. Basically, you don't change anything because for Arduino UNO, they have already made it the default A0 will be an analog input. Okay. Um, so you don't need to do any changes there. You need to, if you need to use that A0 pin as a digital input, yes, then you need to change, you need to use that pin mode function for that particular pin. Okay. So in the loop, what they are doing is sensor value is assigned to analog read function sensor pin. So basically it is reading using this analog read. For digital, I know read, you have used digital read function. For analog read, it is again analog read. So it's very simple to remember also. You use that analog read function, and the sensor pin is read. So basically A0 is read, and that value goes to sensor value here in this. And in the digital write pin, you basically then you are
Basically,
delaying that sensor value. Whatever you have read, that many milliseconds you are delaying, right? So more value you read, more analog voltage you read, your LED will be turned on for more time, right? So it's basically that LED turn on time is kind of a proportional to your analog input read, right? So what I'm going to do is I'm going to use this code, but some portion of it might not be using this LED portion. But I'm going to quickly show you how you will read the value in the Arduino. So again, I'll go to the Tinkercad, or yeah, I don't have the potentiometer set in my Arduino here, but next day I'll set it up. I'll have a potentiometer connected to the Arduino what I have here. But right now, let us see a new one. So I already have this here. So this is nothing but you know example. I have connected. See, this is a potentiometer. Okay. This is a potentiometer. It's a 10K potentiometer. So it's connected to extreme terminals are connected from 5 volt to ground. Circuit is like this. So here is the Arduino. So this is 5 volt. This is ground. So the potentiometer terminal 1 and 2 are connected there, as you could see here. This is the terminal 2, sorry, this is terminal 1. Okay, anyway, it doesn't matter much, but just to have the same nomenclature. And this wiper is connected to A0. This is Arduino UNO, right? So this is the circuit, this is 10K. So what will happen? Okay, so I'm going to read this. So as you could see, this is 5 volt and this is 0 volt. So either I could read, if my wiper is somewhere here, then obviously I will read 0 volt. Okay, and if my wiper is somewhere here, then I'm going to read 5 volt. Very simple, right? If it is in the middle, maybe I will read something around 2.5 volt. 5 volt, right? But as we are converting this analog voltage, so 0 volt and then 5 volt and then 2.5 volt, etc., right? As we are converting this into digital world, right? So this will be obviously in 10 bits of digital values, right? So you will have so 10 zeros basically, right? And here you will have 10 ones, so that because that is a full scale, right? And here you will have something in between. Now what is this and what is this in decimal? Basically, this is 3FF, right? So what is in decimal? 1023. Right. So in analog world, our voltage will vary from 0 to 5 volt. But in digital world, we'll read something from 0 to 1023. Right. And maybe for 2.5 volt, we'll read something around, okay, 500. I'm just approximately, I'm telling, okay. Maybe 510, 512, something like that. Is it understood? Okay. So let's go to the Tinkercad now. Okay, the analog sensor values, the same code what I was showing you here, the example, right? The this is analog input. That is the example file name, and the same code is here. Though I haven't connected an output. Okay, let me connect an output also, and so that output is connected. Okay, that output is anyway the inbuilt LED. So you can see this L, right? So pin number 13 is basically the internally connected to this inbuilt LED. So you will see this inbuilt LED glowing. And at the same time, I want to do mm, uh, serially, I want to read it also, right? Okay, so for that I need to serially, I need to the serial port I need to initialize. And here I'm going to write another line of code. I think it is small only. Okay, so it will serially print the sensor value as well. I think that's all about the code, and now I'm going to start the simulation. Now if I go to full scale, then what happens? I'm getting 1023, which is the full scale. Okay, and this is now very slow blink. And then I go to the other side, other direction. Okay, the value is coming down, and then I go to the negative and it becomes 0, right? And it doesn't glow only. If I increase it little bit, then it's so fast that we are not able to make out that it is blinking on and off, right? Like it is on always, but basically it's blinking very fast, on off, on off, on off, and our eyes are not able to catch it because of the perception of eyes is around 20 millisecond. So as you could see now, see it is now blinking kind of on off, on off, on off, you can see. And here now you can see more, and the values are increasing. Again, I'm going to this side, and these values are more, and also your LED is blinking slower. Is it fun? See, it's so fast you are able to you can read an analog value through the Arduino without even not knowing the ADC, just using this analog read function, and it does everything for you, right? Suppose if you want to connect these to pin number 1, right? Suppose I want to connect another input to maybe A5. Okay, so let's do that. I'll stop the simulation. See how fast you can modify the code also for your application, starting from an example code. That's the fantastic part for Arduino. It's really great. I haven't found that in any other platform that you can start so fast. Okay, let me take another different color wire, and let it be a orange wire. But okay, let us draw a little bit more professional way. Okay, this is our positive. We'll take the black only as the negative and maybe simple connect it here. And this also got changed to black. Okay, and we'll connect this middleware to A5. Okay, and we need to change the code a bit because you here see here again this fellow has used this declaration. This is a good practice to declare your pin always, pin mode even though it is a default one, but still it is better to declare. That's for better readability and it won't cause any confusion later, right? So now my analog input, the A5 is also an input and it's an analog input by default. I need to read it. So maybe sensor value 1, I will declare this as sensor value 1, A0, and or it's better to write it as A0 and this is as A5. Both are initialized to 0. And analog read sensor value, so it will be sensor value A0 you were reading, and again here you will read sensor value A5, that is the variable. Five A0, so I will use just print. So A5, okay. So I'm going to read both the sensors, but okay, I'm driving the LED as of now with the A5 only. Or I can do one thing. So your on will be based on sensor value A0, and your off will be based on sensor value A5. Okay. So basically, I'm reading two analog inputs, one connected at A0, one connected at A5, and the turn on time of the LED is proportional to the sensor value A0, and turn off time of the LED is depending on the sensor value A5. Okay. And I'm also serially printing those values. Okay, here I need to use a new line. So after the sensor values, it's okay. Now let's simulate. Okay. So now you can see that both the sensor values it is giving. Now I'll change some value here. You see the second one is changing here. First one still remains same. And your on off time will be a bit different. Your on time is more, but sorry, on time is less and off time is more, right? And that same appears here. Yeah, now I'm changing it on time more and off time less, right? You can see that in the LED, right? So see, using the example code and writing only some 2-3 line of code, we have built another application. So so any kind of, now if you want to read a temperature sensor or a humidity sensor, which gives an analog kind of value, right? Analog voltage kind of values. This is the way you are supposed to read it through the ADC, and you can use the data to publish somewhere, to send it to the serial port to the PC, or you want to show that in the local display, right? So this kind of applications can be done. Or you want to read some kind of wind bridge output, right? Some analog other values, or pressure sensor, or something like that. So these are the kind of applications where ADCs are useful, and the analog to digital converter function, conversion function of ADC is useful. Okay, so I think I have taken too much time today, but it was useful, I believe. Could cover a good portion of it, and now we at least know the ADC and how we can read the analog values